Hello, welcome to Mechie Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty my God for my good health and broad mind. And I would like to thank my friends, followers, my dear students and subscribers for their continuous support and encouragement of creating these kinds of videos. Today's topic of interest is flow through pipes. First of all, what is meant by flow through pipes? A stream of jet or a liquid is flowing through a closed conduit is called a flow through pipe. A flow, the characterization of a flow in a pipe is called flow through pipe. Okay, let me check. Find the type of flow. I am going to give two images. You are going to find the types of the flow. Yes, these two. Can you guess what is the type of flow? Here, this is one, this is two, this is turbulent, and this is laminar. Yes, it is. Your guess is correct. First one is a turbulent, and second one is a laminar. A turbulent flow is look like a zigzag manner of the flow stream, whereas the laminar is the finite motion. Finite motion. So the two different kinds of this flow you can easily visualize when you see a candle is glowing. If a candle is glow up to certain distance, the flow is like a well defined and well laminar flow. So that is called well defined flow is called laminar flow. After certain region, the flow is make a distracted in a zigzag way. So that is called a turbulent zone or turbulent flow. You can easily visualize these two flows when you see a candle is glowing. So these types of flow is based on the Reynolds number. Reynolds gives a beautiful formula and relation about the type of flow, either it may be laminar or it may be turbulent. He gave a beautiful ratio about the flow. The Reynolds ratio, Reynolds number, is the ratio of inertial force to the viscous force, where after all the derivations, putting inertia force as well as the viscous force, we come up with a formula of rho vd by mu, that is density, velocity and characteristic length divided by the dynamic viscosity. If we can say the dynamic viscosity by rho, which is called kinematic viscosity, it can be replaced by means of vl by nu. Okay, we illustrate the formula. Okay, fine. How the laminar, turbulent and transitions are being given. If the Reynolds number is less than 2300, we put the values of density, velocity, diameter and mu in the formula. We substitute this. If the final value is less than 2300, it is called laminar flow. It is the laminar flow is predictable and slow moving of the fluid jet is there. And if it is the final value is greater than 4000, it is turbulent. It is unpredictable and a rapid mixture is there. I am saying the slow mixing and rapid mixing is in the flow of jet we put an ink we put an ink at the center of the pipe. If the ink stream is straight and well defined and predictable in nature, it is called a laminar. If it mix easily, then it is called turbulent. If the Reynolds number value is between 2300 and 4000, it is called transition. The laminar to turbulent transition is there. So turbulent outburst, you can see the turbulent outburst. And this flow characteristics, flow path is also affected by the surface finish of the pipe. If the wall is smooth, the characteristics are well defined. If the wall is rough, then it will automatically becomes a turbulent zone. We cannot create a laminar in a rough surface, whereas we can create laminar as well as turbulent in the smooth wall. That is why uh, we have changed ourselves from the galvanized iron tubes into a PVC tubes, since it is having a smooth wall while transferring water in household applications or farm applications like that. I hope you have understand what is the Reynolds number and what is the its uses. And now I move upon the flow through pipes. Energy or head loss in through pipes. Losses in pipes. So that is the head losses or energy losses. We can categorize into two types. One is major loss and another one is minor loss. Major loss is by means of friction, the viscosity, and the interaction of the surface and liquid region. So, in this region, the friction is there, therefore, that losses is called major losses. So, it can be estimated by means of Darcy-Weisbach formula, Chessy formula if it is for the turbulence, and for the laminar we can use Hagen-Poiseuille. And the minor losses like sudden expansion of pipe, sudden contraction of pipe, pipe bends due to pipe fittings, disturbances in the pipe, like that, the minor losses can be classified. So anyhow, the major and minor losses are the two losses in flow through pipe. So this is the major loss, the head loss due to friction. Let us consider a straight pipe of having a 2 points, say point 1 and point 2. We have find a length and we put a liquid in flow with the velocity of v. So we found that there is a difference in head between section 1 and 2. The difference in head is due to the layer effect, that is the frictional effect. It can be illustrated here. The effect of friction in the pipe wall on the layer of the molecules can be given very beautifully when a layer which interacts the solid surface, there the layer at most is stationary, and the above the layer is moving slowly, and again above the layer it is significantly slowed and slightly slowed and moving freely, and free water flow is there. Like that, the flow can be modified, and at the center of the pipe we found that the maximum velocity can be attained at the center of the pipe, where at the center of the pipe the flow is free flow, as well as the shear stress in the layer is almost equal to 0. So that is our understanding about the concept, and these major laws is derived by the Darcy-Weisbach. So Darcy-Weisbach formula is, we have two formulas. One is H is equal to F L V square divided by 2GD, and another formula is H is equal to 4FLV square divided by 2GD. If I say F, it is friction factor. If I say 4F, it is coefficient of friction. So that is the difference between those formulas. I have given a formula, a generalized formula like this: FL square, FLV square divided by 2GD. If the F, if it is a laminar flow, it is 64 divided by RE, and if it is a turbulent flow, it is 0.316 divided by RE power 1 by 4 or 0.25. It is a turbulent. I I make a formula instead of velocity v. We know that q is equal to a into v. Therefore, v is equal to q by a. If I put instead of v, I put in the terms of q by a. The formula comes out like this: FL q square divided by 12 d power 5. So this formula you have to remember for the problem solving as well as better understanding. So next is a minor loss. Minor loss in piping system, we know that we can't manufacture a straight long pipe for infinity length. So we are going to make pipe joints or couplings, pipe fittings, valve bends. We cannot do the pipes always straight. We have to bend sometimes. So elbows and bends and T joints, and we have an inlet and exit and enlargement, contraction and addition of the pipes. All the things are came. So in these regions the minor losses is occur. So for an example, coupling, end caps, reducer tees, toes, elbows, reducers, union, close nipple, plugs, Y bend, L bend, T bend, screw cross, 90 straight elbow, long pipe, 45 elbow, return bend, reducer T, elbow union, like this, gate valves. All the things we found the major losses. So here for you, the minor losses. The here for you, the minor, some of the minor losses I have illustrated here. One is head loss due to contraction in pipe, that is sudden contraction and gradual contraction, and the entrance loss, head loss due to enlargement of pipe, and the enlargement also sudden enlargement and gradual enlargement is there, and exit loss, loss due to pipe fitting, loss due to bends and elbows, like that. We have given the formula for finding the minor losses. So here the first one, head loss due to contraction in pipe, the sudden contraction. Usually pipe causes a marked drop in pressure in the pipe because of increase in velocity and loss of energy of turbulence. If the velocity is increased, we know that the Reynolds number Re is equal to rho Vd by mu. Therefore, Re is directly proportional to V. If velocity get increased, Re also get increased. Therefore, if wherever the velocity is getting increased, there a chance of turbulence is there. So head loss due to sudden contraction is been given as Hm is equal to K into V square by 2G, where K is the sudden contraction coefficient. The value depends upon D1 and D2 ratio, D2 by D1. So that is the ratio about the function K, sudden contraction coefficient. Here V2 is the smaller pipe. Contraction means after contraction only the losses are there. So before and after the we can found. Therefore V2 is the appropriate one. And next is a gradual contraction. The same manner, the gradual contraction is also having Hm is equal to Kc into V2 square divided by 2G, where V2 is the smaller pipe velocity and Kc is the gradual contraction coefficient. The value depends on D2 by D1. And next is the sudden enlargement. Here the sudden enlargement we have found some of the eddies are forming. Therefore, we have to calculate the head loss by means of equating the or differentiating the velocities like v1 minus v2 the whole square divided by 2g. So this is the formula. v1 minus v2 the whole square divided by 2g is the formula. And next is the gradual enlargement. The same thing for the gradual enlargement. Hm is equal to Ke into V1 minus V2 the whole square divided by 2g, where the Ke is varies with the diffuser angle. If diffuser angle is, I am saying 10 degrees, the Ke value is 0.08. If it is a 75 degree, it is 0.72. Okay, so next is the entrance loss. Here the entrance loss is Hm is equal to Ke V square by 2g. So the V is the velocity in the pipe. Velocity in the pipe. The K value is being given like how the entrance is being desired, like that the K value is varies. Next is the exit loss. Here also Kd into V square divided by 2g, where Kd value, since it is the discharge outlet loss, the K value is always is equal to 1. Therefore, V square by 2g is the appropriate equation. Next is the minor loss due to pipe fittings. So this is Kf into V square by 2g. So Hm is equal to K square Kf V square divided by 2g is the formula. So for the globe valve, the K value is given and the L by D ratios are all given. So you can pause the video and notice this for your better understanding. Next is the bend losses, head loss due to bend. Here also we have a formula Kb into V square divided by 2g, where V is the after bend velocity and Kb value varies with R by D, the ratio of R by D. Next, after knowing all these major and minor losses, we have a series and parallel pipes. Here in the series and parallel pipes, we have to notice these equations better. If the pipe is series, it is connected one by one. If it is a parallel, pipes are placed parallel about one by one. So if you see a radiator, it is a parallel flow. The flow is being parallel. We have an inlet at the top and outlet at the bottom. The small pipes are placed parallelly, so in order to make a better convection kind of things. So it is a very simple example of the parallel flow. If you see the radiator in an automobile, it is a better example of seeing a parallel flow. For the series flow, a water line to our house from the tank. How it is look like? In a tank, it is a big pipe. In after all our house, we have a very small pipe. So like the series of pipes are being connected and jointed, it makes a series pipe connection, and radiator is an example of parallel flow. Here, one thing you have to notice that in series pipe, the discharge in every section is equal, where head loss is the total head loss is the sum of head loss in each and every section. So that is the interest. And whereas the parallel pipes, head losses are equal, where discharges, for finding total discharge, we have to add an every pipe discharge. So that is the interest about the parallel and series pipe. And next one is the equivalent pipe. So the parallel pipes and series pipes we can make in an equivalent manner, equivalent pipe, like the L by D ratio. So this ratio plays a major role, since head loss is equal to 4FL V square divided by 2GD, or FLQ square divided by 12 into d power 5. Here L by d power 5 ratio will makes an equation. This equation is called duplet equation. So this equation is called duplet equation, DUPLET, duplets equation. So as per the duplet equation, the equivalent length and diameter ratio is the sum of all the length and diameter ratios in each and every pipe. So L by d power 5 is equal to L1 by d1 power 5 plus L2 by d2 power 5 plus L3 by d3 power 5. So on. So here the agenda is, if we have a series pipe like this pipe of having a different length, so say L1, L2, L3, and having D1, D2, and D3. So these pipe can be connected by means of a same diameter pipe of having D as well as having L. So this conversion is done by this equation. So this equation is called duplet equation. So for the better understanding, we have to notice these formulas for the parallel series pipes as well as the equivalent pipe. So with this, I'm going to stop today's lecture. So if you have any queries, please let me know in the comment section, and I will put another video for clarifying your doubts. If you like this video, please like, share and subscribe my channel Mechie Techie with Santhosh for the continuous update about the mechanical engineering. So once again, I thank you all for the patient listening, and thank you once again. Thank you.